Okay, so thank you very much for joining this webinar, Le Lab Quantique, a second online meeting. Today we have great speakers for good presentations. I think you'll enjoy that very much a little bit later. First, I'd like to give you some ground rules. First of all, it's a webinar, so attendees can't broadcast their videos. All attendees are muted at their start. So if you want to talk, raise your hand to the host, so me or Jean-Gabriel, and we grant permissions. Important point is that you can ask questions to the speakers, to the panelists, through the Q&A window that you should find somewhere at the bottom of your screen. Questions are public. Please mention the name of the panelist you're asking the question to. And there's a possibility to vote for the questions, but you put them on top. And they are asked in a way in order of priority. Of course, there are no bad questions, but it's going to be interesting to see these exchanges. I think it's really important that you can communicate with the speakers. We had many questions last time, so we've organized things a little bit differently this time. So after this meeting, you'll have in a couple of days, I think 4 days, the link to the video and also to the presentation. You can find them also on the Meetup website, on our YouTube channel, and on our brand new website. So it's https://lelabquantique.com, where you can find all the information. Again, an introduction about Le Lab Quantique. So we're a Paris-based not-for-profit running a range of initiatives in support of the global quantum ecosystem. We've organized meetings so far in person, lots of conferences with the support of BPI France and the Quantum Nation Fund, investing in quantum technologies. We've organized hackathons, quantum computing and quantum networks since 2018. And we're planning to have many more activities over the next months. So keep in touch with us. It's going to be interesting. Today, we have 3 speakers. LOIC HENRIET, who's a software engineer at Pasqal, will tell us about their technology for quantum computing, make a very nice demonstration about how to compute with atoms. Simone De Liberato from University of Southampton is going to talk about nano-photonics, a pretty inspiring speech and a fantastic or very interesting sector. And Jean-François Bobier will join a little bit later. Jean-François is from the Boston Consulting Group, and he will give a talk on quantum computing for big pharma, biopharma, sorry. Our next meetup, so please take note, will be on April 28th. We have already 2 speakers confirmed. So Mehdi Namazi from a startup based in New York called QNet, and on the components for the quantum internet. We've got Nathan Sharma from Unitary Fund, will tell us about their initiative. It's also a not-for-profit based in the US, and also about open source for quantum computing. And a third speaker, we're in a discussion currently to just complete the panel for next session. So thank you very much again for being here with us today. I'm sure we'll have a great session. So I leave it to Loic to start. And again, remember about the rules, what I said a little bit earlier. You can ask questions anytime. Loic will answer after his presentation. And yeah, let's have a good meeting. The floor is yours, Loic.
Hi, everyone. I will start the presentation. Okay. Hi, everybody, and thanks for the opportunity to talk here about Pasqal, and more specifically, how to program quantum circuits using Pasqal as a backend. First, a few words about the company. Pasqal is a hardware provider. We build quantum processors made of neutral atoms controlled by laser light. And it's a spin-out of Institut d'Optique Graduate School of the lab of Antoine Brouet and Thierry Lahaye in Palaiseau. And several generations of postdocs and PhD students have contributed to the development of the device that we have currently. The device at Pasqal will be accessible through standard quantum computing frameworks like Cirq, developed by Google, and Qiskit, developed by IBM. And the Circ Pasqal interface is officially up and running, and I will show you today how it can be used. So here the outline of the talk. I will first speak about Pascal quantum processors, and then show you how to program a quantum circuit for Pascal using Circ. And in the end, I will present one particular use case of machine learning using TensorFlow Quantum. Okay. So at Pascal, our qubits are neutral atoms that are trapped in optical tweezers. So an optical tweezer is basically an atom, a trap for one single atom. And you have here an experimental plot, fluorescence plot of atoms in our device, where each green dot here corresponds to one unique rubidium atom. And the atoms are held fixed by these optical tweezers by a variety of techniques from quantum optics to laser cooling. You have a popular summary of the technology that is available here on this link, written by Lucas Béguin and Adrien Signol. It is a scalable technology. We can have routinely in the lab up to 100 qubits in arbitrary 2D or even 3D geometries. So here you have real plots from the experiment. So you can have arbitrary shapes like a torus or even Eiffel Tower. And with the same technology, we can hope to go up to 1,000 qubits with the same hardware components. So we have our qubits, and the quantum information is stored in the electronic state of the atoms. So in other words, the 0 and the 1 states of the qubit correspond to two distinct electronic levels. And the interaction, or equivalently the ability to do multi-qubit gates, is possible via long-range dipole-dipole interactions. And that provides us with a large connectivity. A large connectivity means that our qubits can talk to a lot of other qubits in the chip. A few words about the functionalities of the device. The first one is Hamiltonian quantum simulation. And it was the first functionality for which the device was priorly designed. And the Hamiltonian that we want to simulate is actually the function describing how a quantum system evolves in time. And the idea behind quantum simulation is to recreate in the lab some models of interest to explain basic physical phenomena. One particular example is quantum magnetism, the description of how magnets behave at low temperatures. And there are some theoretical models to explain the behavior of these materials, but it's actually very difficult to do numerical checks on standard computers to test the validity of such models. So the idea of quantum simulation is to reproduce in a real experiment the ingredients that are thought to be sufficient to describe these physical phenomena. One then sees in the real experiment if this particular model gives rise to the expected result. So I showed here the Hamiltonian used for quantum simulation of quantum magnetism, but it can be extended to any quantum system, and for example, chemistry, for drug discovery, and even more exotic phenomena like those occurring in high energy physics, for example. And it's interesting to note that the quantum advantage in quantum simulation has already been reached using neutral atoms in this particular paper of the academic group for quantum magnetism. And the subject of today's talk is more about gate-based quantum computing. So the device was primarily developed for quantum simulation, but it can also do quantum computing. So what is quantum computing? So here, the evolution of the quantum system is parameterized by a circuit and no longer a Hamiltonian. And here you can see a quantum circuit that describes the state of 4 qubits from Q0 to Q3. And each qubit state is represented by an horizontal line. And you can apply gates to those qubits, either single qubit gates like this one, or multi-qubit gates, like here, a 2-qubit gate involving Q0 and Q1. And the neutral atom platforms have actually capabilities on par with other platforms, and in particular, great fidelities of gates. And it has been reported in various papers this year and in 2019. So this will be the focus of today's talk. So we have a platform with a large number of qubits, great fidelities, large connectivity, but how to really do a quantum circuit and program it so that it is done and executed on our device. I will show you that today. And to do that, we have partnered with Google, and we have an interface with CHRISTOPHE, the framework that is developed by Google for quantum circuits. So the next part is on how to program quantum circuits using CHRISTOPHE. So as I told you, CHRISTOPHE is considered as a front end of Pasqal device. Pasqal devices can be used as a front end. And CHRISTOPHE is a Python framework developed by Google for quantum computing. The idea for using CHRISTOPHE for Pasqal devices is first to install CHRISTOPHE locally on your laptop, and then to send a quantum circuit to a Pasqal system. And then you can either choose to run the circuit on a real quantum processing unit or on a classical computer, a classical emulator that will reproduce the effect of the quantum computer, but with a limited number of qubits. And then after this procedure, measurement results will be output and given back to you. The one advantage of CHRISTOPHE is that it is compatible with Python packages for applications like OpenFermion for quantum chemistry or TensorFlow Quantum for quantum machine learning algorithms. And right now, the Pasqal quantum processing unit is still under development in a proprietary use, so not accessible to the public. One good advantage of CHRISTOPHE is that it allows a large control over the operations that are actually realized on the hardware. So you can either choose to send us an abstract quantum circuit that is really a simple description of a quantum circuit without any constraint, or try to send us something that is more constrained and that will respect the constraint of the device. So if you send out an abstract quantum circuit, actually this abstract quantum circuit will be processed by our system and optimized by Pasqal software, so that it's not really the same circuit that you send that will be done on the device. But if you send us a readily implementable device and that you specify that you want really this particular sequence of operations to be done, you can also do it using CHRISTOPHE. And I will show you this particular example today, where one programs a quantum circuit that respects the constraints of the hardware and that can be natively implemented on the device without any modification on it. And that can be interesting for research purposes and for benchmarks and so on. Okay, so what are the constraints of Pasqal devices? Well, actually we can do arbitrary single qubit rotations. So for single qubit gates, there are no constraints. For 2 qubit gates, one usually think about CNOTs, but the native 2 qubit gate for Pasqal devices is a control Z gate. A control Z gate is the following one. Here I give the matrix representation of the control Z in a Hilbert space generated by 2 qubits. So here it's the computational basis of 2 qubits. It's a diagonal gate with the -1 phase for the 1-1 state. The control Z has a large but still finite connectivity. What does that mean? It means that this CZ is actually done by a sequence of 3 laser pulses between different qubits. And that can only be done if the qubits are close by. And if the distance between the 2 qubits is larger than a particular number that we call the control radius or Rydberg blockade radius, then you cannot do the control the operation. Okay, so let's jump in and try to create the first circuit. The first step is to import CHRISTOPHE and then to create qubits. So I create Pasqal qubits, which is here just a list of grid qubits. Grid qubit is an object that already exists in CHRISTOPHE, and you just declare this register list of qubits. It corresponds here to a qubits arranged on a grid of 6 × 6. After the declaration of the qubits, you can create a device. To create a device, you instantiate what we call a Pasqal virtual device that you can import from CHRISTOPHE.pasqal. So why virtual? Because here we still have only the classical emulator. So that's what the virtual stands for. But in the long run, you can have with the same syntax other real devices that will be available. So then you create a Pasqal device by calling a particular instance of Pasqal virtual device. It takes different parameters. So the first one is obviously the qubits, and the second one is the control radius that I talked about earlier. So the radius that allows multi-qubit operations between qubits. Okay, so we have qubits and the device. The next step is to, well, write a circuit. The first step for that creation is just to call the circ.circuit object, but specifying the device, specifying that you will use as the device, Pasqal device that you've created earlier. And then the only thing that remains is to add gates to that circuit. So, okay, let's try to add a CNOT between qubit 0 and qubit 1 of my register. And what is interesting is that Circ knows that CNOT cannot be done natively on our device. So it decomposes it into a sequence of different operations. Here it has decomposed it in a sequence of 3 operations, 2 single qubit gates on both sides of a CZ. So that the Circ already knows what gates we can do. And when you try to create a CNOT, it decomposes it automatically. Another thing that I mentioned is that it is impossible to add multi-qubit gates if the qubits involved are too far away. So for example, if you try to add a CZ between the first and the last qubit of the register, that would correspond to these 2 qubits here. It's not possible because the distance between them is greater than the Rydberg radius. And then Circ will throw you an error telling you that the qubits are actually too far away for that operation to be realized. Next, one can add as many gates as you want, and the final step is to run the circuit locally or to send it to our remote server. To do that, you just have to call a built-in object that is a Pasqal sampler that takes as an input the HTTP address where our server is located, and you'll need also a password. And the final step is really straightforward. You just run your circuit with a given number of repetitions that will correspond to the number of times the processor actually does the circuit. Okay, so here I've shown you one particular example that is not really interesting in terms of applications, but one good thing about Circ is that it allows to leverage quantum libraries that are compatible with Circ for use cases, and in particular for use cases that are interesting in what we call the noisy intermediate scale quantum computing era. So where you have noisy circuits of shallow depth that are implemented on real devices. So a few words about variational algorithms. So they occupy a really the prominent place in the NISQ framework. So what is a variational algorithm? It's the objective of a variational algorithm is to optimize for a given objective function. Let's call it C. It can be the ground state of a chemistry Hamiltonian or the cost function of an optimization problem, whatever you like. Then you will use a hybrid algorithm to optimize for this function. And hybrid algorithm with both a quantum processor and the classical processor working in tandem. The quantum processor will prepare a given quantum state parameterized by a set of variational parameters theta. So here I'm showing a circuit taking n qubits as an input and producing a wave function psi of theta, where theta parameterizes the gates that I'm applying in this circuit. One then extract from this state an estimate of the objective function that you want to optimize from measurements. And this estimate is used as the input to a classical optimization procedure. So here you have a classical computer that updates the value of theta to find let's say, the minimum of the cost function C. And the classical optimizer updates the parameter theta so that this loop can be repeated, and it's repeated multiple times until a good estimate of the objective function is output. There's a popular summary of this method that has been written by myself, Leonard Bosning, and CHRISTOPHE JURCZAK that you can find on this link. So as you can see, these variational algorithms really look like neural networks. The only difference is here that the neural network that we're trying to train to optimize a given function is now a quantum circuit. So that's why people often call this approach quantum machine learning, because it's really like a quantum analog of a neural network. And actually, there is it's one of the interesting use cases of real life devices right now. So as it is a method of quantum machine learning, well, you have actually extensions of standard machine learning libraries that have been developed. So TensorFlow is one of the most prominent libraries for machine learning, and Google has developed TensorFlow Quantum, so a version of TensorFlow for quantum applications. Okay, so I will show you how to solve a particular example of a machine learning problem for optimization using TensorFlow Quantum with Pasqal devices as a backend. Okay, so the first step is to import the necessary packages. So Circ and TensorFlow Quantum, TensorFlow, and NetworkX is a package for graph visualization. So I will show how to solve MaxCut. So what is MaxCut? MaxCut is a rather simple graph problem. So here I'm instantiating a given graph that I'm plotting. Given a graph with nodes and vertices, the objective of MaxCut is to find a bipartition of the nodes that minimizes the number of edges between nodes of the same group. So let's see that in practice on this graph, where the two groups are represented by different colors, green and blue. So here is a given partition. So some of the nodes are green, the other ones are blue, and I have 4 edges between nodes of the same kind. But if instead of this having this partition, I look at this one, then you see that you only have 2 of those red edges. So this situation will be favored. So the objective is to find the best possible bipartition that minimizes the number of red links. This particular problem has a lot of industrial applications, for example, in logistics or in scheduling. And one particular example corresponds to the problem of smart charging of a fleet of electrical vehicles on a finite set of chargers. This problem is a subject of a collaboration between EDF and Pasqal. I will not talk about the details of the collaboration or the mapping, but essentially one of the problems that one encounters in this field can be mapped on some kind of optimization problem that looks like MaxCut. In all generality, the MaxCut problem is NP-hard, meaning that it cannot be solved easily on a classical computer. That's why people have proposed to use a variational algorithm to try and solve it. Okay, so let's do that in practice. I will not go through all the syntax that you need to add for solving this particular problem, but the idea is really simple. You have several steps that are well described in the documentation of TensorFlow Quantum. And here I'm solving this particular problem on 2 different devices. The first one is one with a noise model that corresponds to Pasqal. So I'm solving it on the Pasqal backend, classical emulator of a Pasqal backend, not the real device, or an ideal sampler. So what we would get with an ideal quantum computer. And I'm plotting in the end the approximation ratio. So how that it's a number between 0 and 1 that quantifies how good my final solution is with respect to the optimal solution. So 0.82 is the solution obtained for the ideal quantum processor, and 0.6829 for the Pasqal, using Pasqal quantum computer. So the results shown here might not be very impressive, but what matters is actually the scaling of the algorithm runtime with the size of the problem. And if the solution output by the algorithm is reasonably good, and if we can get it in a reasonable amount of time, then that would be best to use a quantum computer. And nothing has been rigorously proved so far about the performances of a variational algorithm for a large number of qubits. So I guess the best way to try to see if it works well is just to do it and look at the results on a real quantum device. Okay, well, that's all for today. The take-home message from my presentation is that there is now a possibility to program quantum circuits with Pascal devices as a backend. We only have a classical emulator available until 2021, and the quantum processing unit is only available for proprietary development use and R&D. One good thing about the partnership with Google and the CERC compatibility is that it allows to leverage packages like TensorFlow Quantum or OpenFermion. OpenFermion is the one for quantum chemistry applications for concrete use cases. You can find more information on CERC on the official CERC webpage and see the details of our custom Pascal objects here. Or if you want more recent developments, you can directly go to my GitHub page. And all what I've described will be developed in more detail in tutorials that will be posted on the website of Pascal in the future. So with that, thank you very much.
Thank you. Thank you, Loic. Thanks for the great talk. Very impressive. Yeah, I think we will move to the next speaker. So Simone De Liberato in a few minutes. We have a couple of questions for you, 5 or 6, I think, or even more at this stage in the Q&A section. If you can have a look, I think it would be great and try to answer that.
Yeah.
I think we're more close to 150 people online, so it would be a little bit hard to take questions directly, but I think it should work fine this way. And again, you'll have the contacts with the speakers later and a follow-on email later in the week with the presentation and the link to the video. Something I forgot to say at the beginning, I'd like to thank Jean-Gabriel Bueno here working with me at Quantonation, who is helping with logistics, because even if it's not in person, I think there are still, as you can imagine, a couple of things to deal with. But for this second meetup, I think we're on the right track now. We understand fully the tools that we're using. And maybe just a few words, I forgot also in the introduction. So I'm CHRISTOPHE JURCZAK. I'm the president of the Lab Quantique, so the not-for-profit that's organizing events. Also partner at Quantonation, so fund dedicated to quantum technologies. We made 8 investments, 2 more to close in the next month in the field. We've invested in Pascal, so I know Loic and the work there really well. But actually investing for us is not really the only reason for these companies to be presented at the lab. And of course, we welcome more in the quantum computing space in the coming weeks and months. So without further ado, I'd like to give Simone the floor for a presentation on nano-photonics. So Simone.
Thank you, Christophe. Thank you very much for having me. Let me check how the screen share works. Okay, do you hear me?
Yes, Simone, can you put on a full screen, maybe?
Oh, yes, of course. If maybe it's fine.
Yes, that's good. Okay.
Okay. So in this talk, I'll discuss a bit. I'll start by introducing a bit the field of mid-infrared photonics, trying to highlight its technological and scientific importance, and then I'll link a bit with my own research and an approach we are championing. Also, we are starting a collaboration with Christophe, trying to exploit novel gravity quantum electrodynamics setups in order to produce a novel generation of optoelectronic devices. So let's start by the mid-infrared. One initial slide just to be sure we are on the same page. We have electromagnetic radiation. It comes in various flavors accordingly to the wavelength. It's always an electromagnetic waves. It's always an oscillation of the electromagnetic field, but accordingly to the wavelength of this oscillation, things can be very different. So we can pass from radio waves, which have a wavelength of the order of the kilometer, to gamma rays with extremely short wavelength of the order of 1/1,000,000th of 1/1,000,000th of a meter. The range I'm going to discuss today is the mid-infrared range, which is just on the red, so with the wavelength just longer than what we call visible light. So something around between 4 and 15 micrometers, which is 4 to 15 millionth of a meter in length. This frequency range, the mid-infrared frequency range, is particularly important for some applications for two main reasons. One is that vibration of molecules, molecules vibrate at mid-infrared frequencies, which implies that by having lasers detectors working in the mid-infrared, we can detect trace amount of molecules in the air. So for example, here in this slide, I show a few of molecules which have specific spectroscopic signatures in the mid-infrared, meaning that we can actually detect them. And I also pinpoint for the different ranges to what this kind of technology is useful for. So at shorter wavelength, 3 to 5 microns, we have all the signatures for water, CO2, CO, a lot of molecules which are useful to detect in order to have ambient air quality and in general atmospheric monitoring. If we pass to longer wavelength, 7 to 10 micrometers, we have more complex molecules, which can be, for example, explosives. So being able to detect them from afar can be a huge asset in the security business. And when we move slightly to a longer wavelength, 8 to 12 microns, we enter into the realm of medical diagnosis. It is today possible to detect a lot of illnesses from very early stage just by scanning the volatile organic molecules present in our breath. So with a breath analyzer, we could detect at extremely early stage a number of very serious illnesses, including lung cancer, and such dramatically reducing its morbidity. Another point of mid-infrared radiation is that the atmosphere is largely transparent in this frequency range. Here we have the atmospheric transmission, that is how much light can pass to atmosphere without being absorbed, as a frequency of the wavelength. And we see, so 100% means that the atmosphere is transparent at that frequency range. And we can see that there are two large windows in the mid-infrared, meaning that if we can realize mid-infrared detectors and mid-infrared communication systems, we can operate them from afar. We can use them for remote sensing, for example. Now, I hope to convince you that mid-infrared radiation is technologically useful. Where we are technologically? Well, we do have very good sources, which are very large. So, for example, here on the left, we see the mid-infrared free electron laser, the Fritz Haber carbon dioxide laser. Those are very powerful lasers. They work very well. are huge and they are very expensive. So they are great for for scientific application, but we cannot think about embedding them in a cell phone or in handheld electronic devices. The free electron laser actually it's a whole building. Another way we use another approach we use to produce mid-infrared radiation is by having nonlinear crystals. So a nonlinear crystal is a crystal that when it receives two beams of different frequency, of different colors, it can combine them and give out the frequency difference, for example, here on the rand omega 2. And we produce by nonlinear mixing an output laser beam at the frequency difference, which can be in the mid-infrared. Here below, I show from a recent paper actually a scheme which has been proposed in the specific to do ultra-fast cancer screening, and we can see in green we have the pump beam. Then it arrives in the block called OPO, which is a nonlinear system, and from there we see a red, which stands for the mid-infrared light coming out. This can work very well. It has the disadvantage, though, that first it's inefficient because you need a very strong pump in order to create the mid-infrared beam. And moreover, you actually need a second laser to pump your device, so it's less than practical. You are just shifting your problem. We know that we have a lot of laser pointer. If I was giving this presentation in person, probably I would be using a very cheap $5 solid state laser pointer. Why we can do that easily in the, let's say, visible, but it's very tough to do it in the mid-infrared. Well, the answer comes from the electronic structure of solids. I will not go into the details, but essentially in solids, electrons occupy different energetic levels, which form bands. And in particular, we have a valence band, which is the last filled, and the conduction band, which is the first empty. And the difference between them is called the band gap. In this picture, there is EG. And essentially, an electron, we inject electrons, the electron falls, and it emits a photon. The photon is at an energy comparable to EG. On the right, I plot the band gap of a number of different semiconductors. And as we can see on the left, their energy, the mid-infrared on the left scale is something of the order of 0.1, 0.2. It's all at the bottom. So the problem is that normal materials have band gaps which are in the visible, near infrared, ultraviolet ranges. There are very few materials, no easily usable material which has a band gap in the mid-infrared. As such, this strongly limits our ability to realize cheap solid-state devices. There was a big breakthrough in 1994 with the invention which is called a quantum cascade laser. A quantum cascade laser is essentially given that we have no natural crystals, natural solid, which have a band gap in the right frequency range, we build one. By now we can actually create, using molecular beam epitaxy and other approaches, atomically thin layers of different semiconductors. And as such, we actually can create an artificial crystal which has the band gap exactly where we want. Quantum cascade laser work very well. By now, it's the only mature integrated technology. The problem is that it's still very expensive, less than the free electron laser. We don't need a whole building. It's still much smaller, but we are still talking of $10,000, $20,000 for a standard laser, which is fine for a number of applications, but not, again, to embed them in cell phone or handheld devices. And this actually, if we look at this fact that actual sources are are normally either expensive or large or cumbersome. So in fact, they are used quite extensively in the military sector to have infrared countermeasures, to blind missiles which are shot at planes, for doing security scanners, for doing, here on the right, we see Alpes Laser, the company of John Feist, recently put on the market this small drone able to do methane detection at 0.1 part per billion. Great, but those are still applications in which with a high unit value and the devices are fairly large. The last one is smaller, but still quite large. It's definitely larger than a cell phone. The next market, the market in which mid-infrared technology is would be extremely helpful is instead the market of to which we can access with compact devices and low unit value. That is the Internet of Things. By now, an over increasingly number of devices is constantly connected to the internet. If we could embed low-cost medium detection, which meant in our fridge, in our cell phone devices, this would really change the world. Your fridge could tell you if your milk has gone off. Your cell phone could do an automatic scan each time by your breath, each time you give a call. Your car could automatically detect, take detection of pollutants in the atmosphere, and so on. The problem is that we need to cut the unit cost of infrared devices by, let's say, at least one order of magnitude. So this was the first part of the talk. I hope to have convinced you that there is an interest in mid-infrared technology. And now I'll sketch a bit the path I've been taking trying to solve those problems. So I'll start by an introduction on what I do. I study polaritonics. I study light-matter interaction at the nanoscale. The first slide has nothing to do with mid-infrared, but will set a bit the stage. If we take a proton is a constituent of an atom, is made of 3 quarks, 2 up quarks and 1 down quark. Now, if we sum the mass of the 3 quarks, we find a mass which is roughly 1/100th of the mass of the proton. Where is the remaining 99%? Well, it is stored in energy. It is interaction energy. The interaction between the quarks is so strong that it gives mass to the 99% of the proton. Now, this kind of physics is normal in strong nuclear interaction. It's called strong for a reason. In electromagnetic interaction, instead, we are not used to having this kind of phenomena because the interaction of the photon, the electromagnetic interaction, is naturally weak. Actually, its strength is measured, is quantified by what is called dimensionless coupling constant, alpha, which is a fine structure constant, which is 1/100, more or less. This means that, what it means that a process with 2 photons is 100 less important of a process with 1 photon, and so on. As such, perturbation theory works very well, which means that we can understand the world around us, thinking of single photons, which perform single interaction with the objects around us. This allows us to, this is the framework we use to describe light as photons which bounce off objects, which are emitted from objects, which are reflected from objects. This is all weak interaction. But we are now able, by using resonator, by using traps, nanoscopic traps, which can take one single photon and squeeze it, trap it in extremely interaction. Think about it as jam. If we have a fixed amount of jam and you spread it on a very large slice of bread, it will not taste much. If you take the same amount of jam and you can compact it, you can put it on a single Oreo, you will feel a much higher density. And as such, photonic energy in that concentration can interact very strongly with matter and lead to new physics akin to what we have in, for example, strong nuclear interaction. This is just one slide, and then I will pass to more applied things. But in this slide, we see the values of the record value of the interaction between light and matter published, reported in the last decade. You see that the record has been linearly increasing for a decade now. So we are now more and more able to create devices in which light and matter interact as never before. And this, for us, gives us a new knob to tune material properties. Now, before we could, in order to tune material properties, we could use temperature, pressure. Now we can also create novel material, novel optical materials by tuning the strength of the interaction between light and matter. And this brings us to the main actor, the main of what I will discuss, which is a polariton. When we have a charge oscillation, so matter that couples strongly enough with light, with photons, those two entities will melt, will create a novel hybrid entity called a polariton. Polaritons are those hybrid half-light, half-matter quasi-particles, and they have been used for a lot of great milestones. They have been used to realize novel form of matter, like Bose-Einstein condensate, to have room temperature superfluidity, and to realize a novel form of lasers, which doesn't require a so-called population version, a polariton laser. Now, all those things have been great successes, but they have all been done at shorter wavelength. So we're using electronic transitions that, as we saw before, are too high energy. They cannot cover the mid-infrared range. Now, charge oscillations. If we look at a solid, at a crystal, in particular at a polar crystal. A polar crystal is a crystal in which silicon carbide, gallium arsenide are materials in which there are atoms of different species. As such, even if they form a crystal, their charge is not uniformly spread. It is, and it forms when the system vibrates, interacts with light. In particular, we have here we have been the scheme in the bottom left. I showed the phonon, the oscillation energies of material we use a lot, 3C silicon carbide. And we see that there are two kinds of those phonons, which are called LO, which stands for longitudinal optical phonon, and TO, transverse optical phonons. Those are charge oscillations which can couple with light. And as such, they can be now used in the same way to create polaritons. Just one slide for the people who are used to work with plasmons. A phonon polariton is exactly the same as a plasmon polariton. Plasmonics is by now a huge field, but where the plasmons, in the plasmons, the photon couple to the oscillation of the electron gas. In our case, in phonon polaritons, the electromagnetic, the photon couple to the oscillation of the crystal lattice. And the properties of those phonon polaritons are, the specific properties are very long lifetimes. So resonances are very long-lived, and we can easily work with them. And moreover, they are very tunable in the mid-infrared range. Those phonon polaritons were initially investigated on flat surfaces by the group of Greffet in Paris, where they actually discovered some very interesting properties of those novel particles. The fact that they actually can emit thermal light in a coherent way. Normally, thermal light is incoherent, is emitted in all directions. If you have a glowing bulb, it emits in all directions. Using phonon polaritons, it was discovered. In 2013, those phonon polaritons were observed for the first time were confined in user-defined resonators. In particular, we see on the bottom left, those are nanopillars, 250 nanometers in diameter of silicon carbide, in which those quasi-particles, those excitations can be trapped. we started investigating this. On the left, you see the trap. It's just a nanopillar of silicon carbide in which those phonon politons can be trapped. And we started investigating how they can be tuned. Actually, we discovered that those are morphological resonances. So their frequency and their properties can be easily changed by changing the geometry of the pillar, or as done by the bottom left by the group of Joshua Caldwell, by slightly doping the silicon carbide. Our interest in this on this material is that the platform needed to realize phonon polaritons is extremely simple and cheap to realize. Actually, only requires dry etch on commercially available wafers. Here on the left, we see our first prototype device we realized. In the center, we have all those nanopillars, each one hosting those phonon polaritons, and the sample is contacted. The two things on the side you see are nickel contacts to have a current flow through it. On the right, we have a sketch of the device, what it should do. We have this current which passes through these phonon to these pillars, excite those phonon polaritons which emit mid-infrared light. First devices based on this mechanism has been realized. Here we have the bow ties and silicon carbide bow tie antennas, so like the pillars, but cut in the shape of a bow tie. This sample was heated electrically, but thermally, and we see that it emits narrow band thermal emitter. So this is already a great first prototype device. Its main problem is that it's thermal, so it is inefficient and it is not possible to do a laser with them. So we are now exploring novel approaches to have a real electrical emitters. In particular, I pointed out before that that there are two kinds of optical phonons, and it happens that one of those kinds is the longitudinal optical phonon is emitted very easily by electrical current. What we call losses, heating, is actually due to the emission of those phonons. The point is that the wrong kind of phonon. So on one side we have the phonon polariton, and on the other side we have these longitudinal optical phonons which are generated by losses. We were recently able to demonstrate, we created a novel entity, a novel quasi-particle using a specific polytype of silicon carbide, in which we are able to bind those three entities together and so create a novel particles which now can be both electrically generated and can emit mid-infrared in the far field. Okay, I'm at my last slide. I hope to have convinced you that mid-infrared technology is a very promising, a very important technological and scientific field, that phonon polaritons provide a groundbreaking platform for mid-infrared photonics that is easy to fabricate and that can really reduce the unit price of devices by at least 1 order of magnitude, allowing us to embed it in user electronics. That there are already proof of concept of technological application, like detectors, like emitters, and so on, and that now we have a promising pipeline for novel future applications. So we hope to turn soon these actual left schematic of a mid-infrared phonon polariton laser in reality. I thank my collaborators by various groups worldwide, in the University of Southampton, in Italy, in Consiglio Nazionale delle Ricerche, in the US, in Vanderbilt, in Germany at the Free Saber Institute, and in Munich at the Ludwig Maximilian University. And with this, I thank you for your attention.
Thank you, Simone. Great presentation. A véritable tour de force, I'd say. Quite a lot of physics and very interesting. I think probably many people in attendees today find it a little bit weird that that's something else than quantum computing or even quantum communication. But I think it's rather clear to me or to many that quantum technologies will have an impact first in quantum sensing or other applications in the short to medium term. And I think there's an incredible potential there, and people should be aware of that. So it was a great presentation. Thank you very much. We'll always have some things to say about quantum sensing and quantum technologies. We'll see you soon. Thank you. Thanks, Simone. And now I've got Jean-François Bobier from Boston Consulting Group. Jean-François will tell us about his research on the impact of quantum computing and new computing technologies, I'd say, on biopharma. He has published a report which is widely known, I think. I might share the link maybe in the in the chat session. So Jean-François, the floor is yours for about 30 minutes. Thank you.
Thank you very much. So after this very scientific presentation, I feel like I'm going to be a little bit more business, and I hope that I won't disappoint this audience. Thank you, Christophe, for inviting me today. So I'm Jean-François Bobier. So I'm a partner and associate director in BCG Paris. I have an engineering background in France, as you know, our Grande École, they are also very involved in scientific education, but I don't pretend to have a PhD in quantum physics, so bear with me. I will be using relatively more simple concepts today. So I'm from BCG. So BCG is a strategy and management consultancy. Really, our mission is to help our client to what we call realize their competitive advantage, and so we're helping them in a different, very wide range of things. Can be organization, it can be strategy, it can be implementing projects, and what we hope to do here regarding deep technology and quantum computing in particular is really help them, guide them with the technologies that are available and that the wonderful startups we are seeing are developing, and to really help them making a good use of them and as early as possible. It's not so easy. You might talk to some of our clients, but you will see that there are, even in large companies, there are different type of people, and the decision makers might not be always the people who are interested in the technologies. And really, we see our value to help your technology to be presented and to be put in the context of a business decision maker. So this is really what we want to do and hope to do. So we've been publishing a lot on quantum computing. It's a technology we've been following since 1998, and we have still a strong publishing pipeline for this year. Of course, COVID has been a little bit upsetting our plans, like a lot of people. But we were a little bit in advance when we wrote this paper in December 2019, how now quantum computing could help pharma. So before everybody asks a question, unfortunately, the quantum computers we have today are not able to help fight COVID right now. Unfortunately, the paper was more predicting a time frame after 3 years, and I will explain you why later. But it could be a significant weapon to have in our arsenal for the next pandemic, hopefully, if we have enough time to develop the quantum technologies we need before that. When I talk about quantum computing, I really think about two, important favors. The first important one, I think, is Richard Feynman, and everybody heard about him. He's a Nobel Prize winner. He was the youngest team leader in Los Alamos. He was actually in charge of computing the critical mass of the atom bomb that was dropped in Hiroshima. And I think it gave him a lot of insight about computation. about classical computation. At the time, of course, he was using magnetical device, mechanical devices, but still it gave him a lot of insights about how they work and what are their limitations. And of course, the second, I think, important person, we are not going to talk a lot about him, but there are a lot of use cases around this. He's a mathematician, he's Peter Shor, and he looked at quantum computers and he said, actually, it's about probabilities, it's about matrix calculations, and a good mathematician can do a lot of things about it, and he came up with a Shor algorithm, which I think really helped the quantum industry take off, because it generated interest from the spying agencies such as the NSA. Unfortunately, or fortunately, they still, I think, are responsible for a lot of funding today. So, but let's talk about Richard Feynman, and I think we are interested in Richard Feynman because his insight is really useful for pharma and chemicals, because basically he introduced quantum computers to say a very simple thing, to say, okay, if I want to simulate nature, I need to use quantum mechanics to do that. And again, he knew very well the difficulties to do it on a classical computer. He stumbled upon them when he worked in Los Alamos with that, and later. There are tons of proof, but this one is probably easy to understand, to show that, let's say, if I want to solve the Schrödinger equations and compute the energy state of molecules using a classical computer, well, I could do it for water, which is very simple, just 3 atoms and not many orbitals. So the atoms are actually very easy because there are 2 hydrogen atoms. They are very simple. It could be a matter of seconds on a good calculator. Okay, that's good. Now, if I put a little more atoms, and now I want to do it for methane, then I need hours, and I probably need an iPhone to do that. Then if I go for more complex molecules, but not too much like Android, it might take years, and I'm talking about HPC cluster to do that. Now, on the right-hand side, if I want to do it, let's say for a protein, and as you know, proteins can be in the hundreds of thousands of atoms. Well, I just can't do it on a classical computer. It will take more time than the edge of the universe. Some people are even trying to evaluate the number of transistors that would be needed to do that, and we would theoretically need more transistors than there are atoms in the universe. So it's not a calculation that is possible on a classical computer. So some of you will tell me, yes, it's true, but it's true if you want to solve exactly the equations. What is going on, and we will talk about it later. Of course, what people do is that they don't compute exactly the equation. They use approximations, and sometimes there are good enough approximations. And even for proteins, we are still able to do some computation on classical computers. But bear in mind, they are not perfect. They are not predictive. They are as good as the data, for instance, you feed them. So for proteins, for the moment, for protein binding, the best algorithms use machine learning predictions to do that. And they are as good as the models that you put. Another problem we have with quantum computers, and I think that's why the 2 previous presentations were very important, is that if we are really looking into pure digital quantum computers, it's still going to take a long time, and it depends on who you talk to. Some vendors will tell you we will have very good computers in 2025. I won't name the companies that tell that. Some are much more pessimistic. They say, no, it's more like 2025. Well, nobody really knows. But let's say we see a consensus that it will probably take a decade to really get to a very important milestone called error correction, which is a game changer milestone because it will allow us to do computations that are precise, that are exact. In the meantime, we will have to live with an era called NICS, which stands for noisy intermediate scale quantum. So it's going to probably last a decade, more or less. So between now and 2030. And during that time, we will have to live with a relatively low number of qubits, with a connectivity that might be not so good. So which is why the Pasqal machine is very interesting, because when connectivity is low, so meaning when qubits are not connected with one another, or you need to swap to be able to do computations with qubits that are far away, you lose a lot of speedups, because what you want is exponential speedup. But if you lose the speedup because you need to switch qubits, it's a problem. So having a high connectivity is important. Of course, gate operation time is important, and there are tons of technology. So, for instance, superconductors are better. They are able to, you can pass a gate quicker than, for example, a trap-ion, which is much slower, about 10 times slower. Fidelity is also important, of course. The higher the fidelity, the better you are, the less noise you introduce each time you make a calculation. And another thing is the lifetime of a qubit itself. Some qubits don't last very long. And the problem that we have today during the NISQ era is that of all of these factors, we have to do trade-offs. We are not able to get, we can get a lot of qubits, for example, but with bad connectivity, with bad fidelity, or we can get a low number of qubits. So, for example, the Honeywell computer that has been introduced recently, they only have 4 qubits, but their gate fidelity and qubit lifetime and connectivity is much higher than other technologies. But gate operation time is slower. So there is no perfect solution right now, and we have to accept that during 10 years we will be in this NISQ era. This is important when we talk timeline for pharma, because the promise is very high, but we will have to live with this limitation for quite some time. So now let's talk about pharma, and I think COVID has really let's say, put a spotlight on some of the difficulties that we are facing in pharma right now, which is that it takes a long time and it costs a lot of money to develop a drug. Now we are talking about 13 years to develop a drug. It's too long when we have a pandemic like the one that we are facing right now. So everything that you see that is tested against COVID is not a new drug. It's actually what is called drug repurposing. So they take existing drugs and they try to use them for COVID, but they were meant for another use case actually at the beginning. But in the future, we might want to be able to design a specific drug specifically to target a specific receptor. Today, we just can't do it. It's just not possible. The productivity has been declining. So for pharma companies, they less and less are able to find new drugs, and it's a problem both for their profitability, but I'm not complaining too much about them. It's more a problem for us because in the past decades, there are not so many new drugs that have been found. And there are still many important diseases like Alzheimer, where we still don't have drugs, for example. Of course, there are problems in terms of reimbursement, so we need to come with better ways to develop drugs, more effectiveness, more cost effective, because we can't accept drugs that are expensive. In the US, there are some drugs that are worth up to a few thousand, $100,000 per dose. I mean, it's too expensive. And of course, there are all new techniques that are available on the market, that will require new techniques and probably new computing power. And this is where also we think that quantum computing can play a role. And there is a significant trend in pharma, which is biologics. So in pharma, traditionally, the pharma companies, especially if you take France, France was Sanofi, and Sanofi in a long time was called Saint-Labo. And Saint-Labo was actually a chemical company, and Bayer also the same, was a chemical company. And they started as chemical companies, and they were discovering that some of the chemical compounds were having a health effect, sometimes bad, most of the time bad, but sometimes good, and they developed drugs based on that. There is a rising trend, which is drugs that are based on proteins. And remember the slide I showed earlier here, proteins are, in terms of computing power, much more complicated to model because proteins, they have hundreds of thousands of atoms, and they are not at the grasp of the current machines. It's just not possible. Today, we only do machine learning, but machine learning is not very good for proteins. So protein is really a new era. And for instance, if you take again COVID, there's a lot of very interesting treatments around antibodies, and antibodies are actually proteins. And today we need to develop them the old-fashioned way, I would say. So basically taking them from infected patients that have recovered and trying to replicate them. And of course, there are new entrants, and for pharmas, seeing that Google is entering the pharma market is a big marker that something is going on. If Google is coming, that means that pharma is probably becoming more a tech business than something else. So, so again, COVID is interesting because it has shed a light on the drug development process. And here you see it, how it works. And as you can see, it's 13 years from left to right. And unfortunately, if we really want to make a change in pharma, and I would like that we enter this discussion after COVID, we will need to look at optimizing this pipeline from left to right if we really want to make a strong difference. The paper we wrote before COVID was focused on the blue part, and this is what we will talk today. But there are benefits also we could imagine on the development parts. But the benefits we will have to see in development parts will also depend on the regulations, and will also depend on our capability to understand the human body better than we are today. So today we have a very limited knowledge of the human body, meaning that here on the blue part of the diagram that I show you, where I develop the drug. So basically on the blue part, I know a target. So I know, for instance, if I take COVID, there is a receptor called ACE2, and I want a drug that blocks that receptor to prevent the virus to replicate or to infect the patient. So I know the receptor from a chemical standpoint. And then all the objective of drug discovery is to develop a molecule that will bind to the receptor and block it. So then COVID will not be able to replicate or will not be able to infect the patient. And this is what we want to achieve on the drug discovery part, right? And this is the objective of drug discovery, is to find drugs that block specific targets. But as you can see, the drug discovery part takes a long time. So it takes about less than 5 years. But still, there's a lot of time after that, preclinical, and then phase 1, phase 2, phase 3 trial. And for those who are following what's going on with COVID, preclinical is to test on animals that the compound that has been developed is not harmful on animals. Then phase 1 is to test if it's not harmful on a few humans. Then phase 2 is to test if there is some effect on a few number of patients. And then phase 3 to confirm the finding on a huge number of patients. So as you can see, it takes a long time from the moment you find a good drug to the moment where you are sure that it does not create, it's not toxic, and it has a proven benefit against other drugs or against placebo. And this is probably again a process that we will need to think again after COVID, at least in a pandemic situation where we will need to reduce that time frame. And to do that, we will need deep tech. Quantum computing will play a role, but we will need other deep tech like nanotechnologies, like the quantum technologies that has been described. So for instance, to analyze better what's going on at a molecular level, to come up with better models and to be able to cut the timeline without compromising the safety. So the promise of quantum computing on drug discovery is to reduce, of course, the time frame, and but that's not the only benefit. Is of course to find more efficient drugs, because the idea here is, okay, I know the target, and to find the best molecule that will bind the receptor and that will do it better. There is also another thing, and that pharmas are not really good at it, is to do de novo drug design. So basically, if I have a better way to predict the relationship between a receptor and the binding drug, and I can do it quicker, then I can do variation of drugs more quickly, and I'll explain what I mean later. And I will able to do the holy grail of pharma, which is de novo design. So drugs that I don't know, molecules that I don't know. So today, pharmas use what they call libraries of molecules that they have, but they know that they are stable and so on. And they start with the libraries and they test them against the targets. But they have difficulties to generate new molecules. And with quantum computers, we could imagine that we could generate more molecules. Of course, those molecules would be better, but for them to be better, we would need to have a better model of a human body. So, for instance, we would need not only to test our drug against the receptor that we are aiming to block, but against a list of receptors in the human body that we know create toxicity problems. So we are able to screen them and to remove them from the test and stop and focus on those who don't create toxicity problems. So if we were able to do more calculations with better models, we would also come up with better drugs, which is important. And of course, if we are able to have a better understanding of what's going on in the human body, we would able to to have more trust in what's going on in clinical trials, and we would be able to reduce the time of the clinical trials. So now, talking into the time frame. So remember what I talked to you about. So we're going to live with NISQ for quite a long time. And we think that NISQ we will see benefits coming from NISQ in pharma in probably around 10 years, maybe 5 years, where we hope to see some speed ups coming from, let's say, for instance, better, drug screening or drug prediction, or where one area, or better prediction to help algorithm in protein binding predictions. So we think that NISQ could play a role there, and of course, the closer we get to the end of the decade, the more qubits we will have, the more error mitigation we will be able to do, the more algorithms we'll be able to do. And of course, we think that we will have a strong advantage, and let's say the revolution will really begin when we will have the error correction milestone I was mentioning later on. So probably in 10 years from now. And in 10 years from now, we can hope much more revolution coming. Now we have to live with what's going on now, and we have to make some progress. And we think that there is a lot of research and a lot of benefits that we see from what we call quantum-inspired CAD. So CAD in pharma means computer-aided drug discovery. They are basically the tools that they use for in silico drug discovery. Quantum-inspired basically means that I use quantum mechanics and I use techniques inspired from quantum mechanics. So for instance, thinking in probabilities, going back to the Schrödinger equations, and simplifying them to get to results and to come up with better algorithms that run on classical hardware. And what we're going to see in the next 5 years is a lot of innovation that will come on that front. And trust me, I come from a classical computer science background. My first job was I was a computer scientist at IBM. I was developing software, and I was used to think in procedural way, step A, step B, step C, and in a deterministic way, and thinking probabilistically, thinking quantum mechanics is a complete different paradigm, and it has opened up a complete new type of algorithms, and there are a lot of startups that are exploiting that. And we already see strong benefits that I will show later here on this diagram. So on the green part, you see the best algorithms that exist today. So DFT is the most used algorithm in pharma today. So it's what they use for large screening. So when they want to screen, let's say, 1,000 molecules, for example, or 10,000 molecules. So they use a technique called DFT. So it's very fast. But the predictivity is not very great. So you might have false positive and the other way around. So it's not a problem when you have a false positive, because you can always test them in the below and say that okay, it was supposed to bind, and it doesn't bind, and okay, you can check it. It's more a problem when the algorithm says it's not going to bind, but actually you have a perfect molecule, but DFT says no, it's not going to bind, and you lose it. And that's a problem today. There's maybe a lot of good candidates that are lost because today the techniques are very, let's say, the predictivity is not very great. There are better techniques. There is one called coupled cluster, but they are very computationally expensive. They are all to the end of the power of 4 for those who are interested in computer complexity. DFT is more O to the log n, n log n actually, to be precise. So it's much faster. And the coupled cluster, it requires a lot of computing power. They've been using techniques like coupled cluster for COVID on supercomputer IBM found 77 compounds to fight COVID using coupled cluster recently but it was on 300 million supercomputer. So it's not something pharma companies can use. For the moment, what we think is that we will use quantum-inspired CAD, and the nice thing about quantum-inspired CAD is that you can have the same accuracy of DFT, for example, but you can do more, or you can increase the accuracy of DFT, but do more screening. And in the long term, there are two candidates for quantum computing. One is quantum machine learning, and there is the research. Companies like Krakow are researching it. And of course, the holy grail would be FTQC on my graph would be fault-tolerant quantum computing, and here you would get the exact result for the screening, but it's more a long-term prospect about 10 years or so. So I think I went for most of the discussion, and I'm a little bit using more of the time I was there. But let's say what we hope is that quantum computing will help, and this quantum-inspired algorithm will help to go to a much agile drug discovery process. So we hope that we will be more in loops, agile loops to develop drugs. We hope that we will test much more compounds, 10 times more compounds. So let's say 100K compounds instead of 10K compounds, which is a big change. So to fight disease like COVID, it will be a big change. And another thing that we think is that we will combine those techniques with machine learning and reinforcement learning to develop new drugs and to use techniques that we see in reinforcement learning, where we do stochastic gradient descent. So we will evaluate drugs not only on affinity, but on other factors like toxicity, like stability, I will explain. But basically, it will give you a score of a specific compound. And based on that score, you will be able to say, okay, I am far. I will be able to draw I will be able to draw a map of compounds, and I will be able to see which one are closer to where I want to go. And then I will be able to do reinforcement learning. So basically generate new compounds that are close to where I want to be, and do the variations of compounds, and basically go to a minimum. And this minimum would be the compound that has good affinity, low toxicity, easy to synthesize, that is stable in the human body. And I think quantum computer could open that. So, but we need a much better prediction engine to do that kind of reinforcement learning approach. But I want to give you this picture because this is, I think, the future of pharma. It is not, unfortunately, it's not for today, but let's hope that for the next pandemic we will be there. Christophe, I hope I was not too long, but
No, it was fine. A great presentation. I think. Thank you very much. I remind everybody that we had Jean-Philippe Picmal from Qubit Pharma 2 weeks ago gave a presentation as well on what he's doing, and he's creating a company called Qubit Pharma.
Qubit Pharma is on my slide, as you can see.
It's on the slide here. That's why I say I see it here. I think it's a great presentation, and very enlightening about a very important application. I think it's interesting also not to overdo it, not to oversell quantum for drug discovery. We've seen some weird things, some weird statements. I think in the field it's of no interest for nobody to go to and claim things that are obviously not true. So I think this kind of presentation, what we're doing with the lab, is also, in my view, quite important as well. I think we must be realistic, and we must understand and not oversell, absolutely no way, the power of quantum computing for drug discovery.
Exactly.
Okay, so I will just show again. So the slide about our next meetup. So thank you to our speakers for the presentations. I think it was great, as usual. Appreciated that very much. Thank you guys. Had a lot of questions as well. Our next meetup will be on April 28th. Again, we'll have Mehdi from QNEC, Nathan from Unitary Fund, and a third mystery speaker as we speak, who will join the panel. What we try to do is have some discussions with startup founders. Maybe in this case, we'd like to talk about the ecosystem, tools as well. Nathan will tell us about his initiative and open source, as I said. And I'll talk about science as well. I realize it's a bit harder sometimes, but I think you need to dig into the science and the physics to understand a bit the fabulous potential of quantum technology. So I think it was great to have the three of you today, and we try to keep such a high level for the next rounds. You should all receive, so attendees, a mail, I think in 4 days in principle, it's programmed, with the links to the video replay and the presentations. Or you can find them on our website, labquantique.com. It's brand new. It was put online this weekend, so you can have a look. And there's the YouTube channel. So many ways to find the information. And if you want to connect also with our speakers, of course, I'd be happy to share the contacts. And thanks for the great questions, great interactions. Thank you very much. And looking forward to see you next time. And I would say a big round of applause for our panelists, but it would be a little bit weird. So thank you very much, all of you. And let's keep in touch. Thank you.
Thank you.
Thank you.